So we're picking up with our discussion of Ethernet concepts right after we talk about Ethernet cabling here. So let's move on to how Ethernet puts its frames on the wire. Ethernet uses a protocol or a method of accessing the wire called CSMACD. And that's a big long string of alphabet soup there, and it basically stands for Carrier Sense Multiple Access / Collision Detect. So let's break down this phrase into its constituent parts, since that's really the easiest way to go about it. Carrier sense means that Ethernet will detect whether or not a cable's plugged in. Obviously, you can't transmit frames across a wire that's not actually physically present. So there is a carrier, there's a carrier wave, if you will, that goes across your Ethernet network, and that is how Ethernet knows, hey, I can actually send packets or frames across this media. Multiple access is just what it says. You have multiple computers that can access the same Ethernet network at the same time. You don't have to have one cable run to a single computer, and that's the only computer that can talk on that segment. Although you can do that with some of the higher end switches, but for Ethernet fundamentals, multiple access means everybody can talk just about at any time. And collision detect is a method that Ethernet uses to prevent multiple stations from talking at the same time. So let's talk a little bit about how collision detect works. Basically, it's a flowchart, if you will. First, it senses carrier, basically, is some other station transmitting. No one else is talking, so I can actually start to send my packet. If not, send the first bits of the frame. Was there a collision? And it can detect a collision based upon the fact that there's a higher voltage on the wire than it should be expected. If so, back off, wait a random amount of time, and try again. Now, this random amount of time is really the heart and soul of the collision detection algorithm. If there were a standard amount of time that a workstation waited on the event of a collision, then you would simply have each workstation backing off, waiting the same amount of time, and trying again. In this case, each workstation backs off, waits a little bit for the other workstation to finish sending its data, and then it starts to try to send its data again. And this sounds really kind of unwieldy, but to be honest, all this happens in a matter of milliseconds or microseconds, so you don't really see any degradation in performance from these collisions unless there's like hundreds and hundreds and hundreds of them, like if you have a duplex or speed mismatch on a port, or if you just have a collision domain that's so huge you've got 5,000 computers in the same collision domain, and nobody can talk because all the broadcasts are always colliding with each other. So if no one else is talking, if there's not a collision, then continue transmitting and just loop through here, send the next bits. Was there a collision? Yeah, there was a collision. Okay, I'm going to back off. I'm going to try sending this frame again. And it keeps doing that, sending a little bit. Hey, was there a collision? Sending a little bit. Was there a collision? Until the entire frame gets on the wire. The best analogy that I've seen for this is that it's kind of like guests at a dinner party. If you've got 8 people around a table and they're all talking, say 2 people start to talk at the same time. Well, they each recognize, hey, I don't need to interrupt this other person. He's trying to talk, so both speakers will stop, and hopefully one of them will time out first, if you will, and start to say their sentence first so that everybody else can listen to it. So lastly, let's move on and look at the layout of an Ethernet frame. Now, here we have the old-style Ethernet up top, and we have the IEEE 802.3, which is the Ethernet 2 standard here at the bottom. And you can see that the frames look pretty much the same. Really, the only difference between the two is this section of the frame right here. In the original Ethernet, this was the type, and in 802.3 Ethernet or Ethernet 2, this is how long the frame is. And you'll recall that part of the preamble or part of the other fields in the frame tell the LLC sublayer of the data link layer what type of protocol is being held in the payload part of the frame, the data part that you see over here to the right. In the original Ethernet specification, this type was encoded directly into the Ethernet frame. And of course, you have the destination address and source address. And of course, you have this frame check sequence at the end. And what that's used for is data integrity. Basically, when a frame is transmitted, the sending station computes the frame checksum and embeds it into the Ethernet frame. It's sent across the wire. The receiving workstation then computes the same checksum, and if they match, then it knows, hey, the frame was not corrupted along the way. If it doesn't match, then at layer 2, the receiving station says, hey, I didn't get all of this frame. You need to resend it. And of course, this is an oversimplification of the Ethernet frame. We'll delve a little more into the inner workings of the Ethernet frame when we talk about VLANs and trunking elsewhere in this course. But for the time being, this concludes our discussion of Ethernet concepts.